Hello guys, how are you? So, now we are in the last module of the thermodynamics part of the principles of thermodynamics, and we are going to comment today on the Mollier diagram. Moller's diagram. It is widely used when we want to study cycles or machine cycles, and it represents all the various state variables that we have seen. We've already seen that temperature, pressure, specific volume, specific enthalpy, titer, specific entropy. So all of this is encompassed in Mollier's diagram, and this will be important for us to study the points where the machine goes without an operator, high pressure, low pressure. How do we manage to extract the power from each of these points? And Moller's diagram is an excellent one. It is an excellent tool for us to start studying. So, basically the great woman. It is built on two axes, the x-axis, the y-axis, and it can be represented in a series forms. For example, on the y-axis we can have pressure, but we can have temperature. On the x-axis, we can have entropy, we can have enthalpy, you can have volume. Then you can build the diagram from a series of shapes. The most commonly used are temperature, with entropy, temperature on the y-axis, entropy on the x-axis, or pressure on the y-axis and enthalpy on the x-axis. And now that we're seeing here within this x-axis, y is a symbol for the case of steam. This is a region. It is the region where we study the behavior of water. So she will have this behavior there that we will understand from now on. The point at the top of the bell is called the critical point. In this region of the critical point region, this region where the water is, it coexists, a condition that we call criticism. It is neither liquid nor vapor, or it is liquid and vapor at the same time. It is a critical condition for the component from this region. Here we don't know how to identify what it is. What is the physical behavior of the water in it, and it is called a point, critical pressure. So, down here, inside this bell, we will have a liquid and vapor behavior to the right side. We're going to have steam on the left side. We will have liquid. So let's start here with the isolate end. How's the Moller's diagram? It is always based on equal conditions. Here, for example, what we are calling barrels is where this means. In this region, the pressure is always constant, which here, for example, the pressure has a bar. Okay, that in this region pressure 10 bars. Here, pressure of 100 bars. So we can understand why here the critical point is greater than 100 bars, with a certain amount of enthalpy, and you are in a critical point condition. But let's go from the determination of the barrels. We will raise this in topics. So for this diagram that we have here, entropy as values n, starting at 400 kilograms of oil per kilogram, and then we build values on top of R's measurement. So, look at the next one. The next information is isothermal. So the esoteric ones are this one point within the diagram, where the temperature is always constant. So you see, in this region that I took, here is an example 100 degrees of temperature, it reaches this point and remains constant until this point and then it descends. What does this mean in this condition? Here from 1 and 100 degrees? Look, we have here the evaporation of water in this condition, so we can determine here by the diagram, but only by this information, by the Mollier diagram. What is the initial temperature condition for us to be able to evaporate water? How many kilojoules per kilogram do we need for water evaporation? Maybe go down and read it here the same way we're going to read it when it completely evaporates this liquid region of vapor. The time she arrives here will not turn into steam. We can know what the value is for total evaporation. So this enthalpy delta is the necessary condition for us to do it. The evaporation of the liquid evaporates. In the same way, we can see the title in this graph. Remember, if here is the biphasic region, which is the liquid plus vapor region, here, it looks only as a liquid region, but we will have the title. And then we start remembering our little equation we saw already in module 7. What is the title, which is the mass of vapor, divided by the mass of liquid plus mass of vapor? So for the pressure of a mass bar of liquid 100 pounds plus steam, 0 bubble point. And we are making an example here. 0.1, 0.2 also on these curves are the tidal curves, where the tidal remains with value of equals 0.5, so 0. So we can do it. Predict with great accuracy. For example, I've got the tidal here. I want the tidal from steam 0.8 to 10 bars. Pressure. It's exactly here. For me to achieve this, I will have to take this condition, and this condition will remit me an enthalpy value here, okay? And that I will also have to know. You have to determine here what the temperature is. The temperature will be in the middle, in. An isothermal here that will rise. And then I can know for a pressure of 10 bar with the title of 0.8 with the enthalpy that I need. What is the temperature that will be then? It's a very big facility. Use a Mollier diagram, then. May you be 100% is the final part here of the bell. Then notice the bell. It starts here with title 0. It reaches the critical point. From now on it will become 1. That is, from this region. Here liquid, that is, the liquid. Saturated liquid rises, cooled, here. This region here is saturated liquid. That region of saturated steam is that region. Here all the liquid plus steam. So we will have the title from now on. We're going to have steam there. People, there's liquid and here, liquid plus steam. The alcoholic iso then are in volumetric iso. Here the volumetric iso they show us what the specific volume is. So in the beginning, if we are going to take it here basically for any pressure, we know what the specific volume is. Let's imagine here for no more pressure, shall we? We can identify it for 1 by an enthalpy of 2600. We have here the specific volume. Likewise, the specific volume. He will, trying, as that, we will, coming down the pressure on. Then you will see that it is interesting. At the end, here you see that the volume is always increasing. Then, finally, 1.68. So let's imagine that we have a volume that is 1.68 cubic meters per kilogram at this point, and here we have a volume that we can read from this line here in that's this whole curve here of 0.02, basically at 0.02. So look at the difference in the size of the volume expansion. There's nothing like the pressure of a bar. We start with a very small specific volume, whether it is about 1-2 liters per kilo, and we end up around 1,680 liters per kilo. But a violent expansion stops when we inject it into the sink, increasing from 600 kilograms per kilogram to 2,600 kilograms. So, thus, an increase in enthalpy does not necessarily imply a specific increase in volume. In this case, we are studying. Finally, there is another, extremely important variable that entropy specifies, and that's it right here, our iso. Entropic. That too, EH. We notice that the value of the entropic iso and we go building entropic iso on top of the chart. So, if we think about the number from Carnot's machine, or even if we think of one ideal turbine, we have to work on top of an entropic iso, then it is IR and entropy values that cut the diagram of Giuliano. Thinking here, for example, is just an example. It's very easy for us to start understanding. Let's take steam here like this, without pressure under, and he will contain this one. So that's it, this entropy here. If I were to produce, and then I would have this amount of enthalpy here that I don't have here, in the case here, which I didn't put, but the X value of enthalpy, and I'm in this condition. It means if I'm in this condition, notice from this region here to here, this here is superheated steam. So I'm in a condition of superheated steam for me to take this machine to a condition of extracting power from this machine. I'll work within an entropic iso when I get to this condition. Here there is already a saturated vapor condition, isn't it? And I'm already saturated with a title 1, i.e. 100% saturated steam. It's easy for us to understand here, but as I still lower the pressure of my system, let's go, I'll start to make the vacuum. I'm with the value here below in atmosphere here. What would the pressure be? Let's say I'm in that condition here. Look at this point here. Look, so I worked on my machine from here to here. What do I have as a title here? Look, if I pull here, look, I'm going to have a tighter, around 0.9, that is, 90% of the superheated steam that I put here at 90%, right? It is in the condition of steam over steam for another 10% of it has therein. Liquid condition means what? You know, that if we put a turbine to operate at 100 kilos of pressure, if we go down in the entropic iso to a vacuum condition in the mold, here it is less than a bar, right? And when this steam is mandatory, it reaches the turbine condenser. That is, it is the exhaust fan. We are exhausted from the machine. I will necessarily have a title on this steam. This is interesting. We work in an entropic iso condition, that is, in the condition of an ideal turbine. So, all this is why this diagram is very important for us to start studying the behavior of from the turbine. We have an example of the diagram that we are going to take as an example, the discharge of a High-pressure water pump. This high-pressure pump is basically this pump here that this pump makes. It will take the condensate from here. That is here with the vacuum. The vacuum will be pressurized to throw into our boiler, where the pressure, which is high, does not compensate. They will take that suction from the pump. 1 kilo. Let's say our condenser is at atmospheric pressure, so the temperature is 100 degrees. Where do we find this guy there? 100 degrees? Look, so the pump is going to be operating in that condition. So this right here is the enthalpy of the condensate around 400. It is something that is already worth per kilogram. Well, so here we have as state properties. The pressure 1 kilogram, the temperature 100 degrees. The tidal is 0 here at that point. There, tidal 0. As I said, enthalpy specifies the specific volume on the order of 1 liter per kilogram, and entropy specifies 1.3 kilograms of oil per kilogram. So that's it, folks. This is the explanation of the Mollier diagram. No, we have seen so far all the material, all the state variables that we need to use to work with turbine calculation is the next module. We will then begin to see the sizing of the turbine sizing machines.